Is it working now? No, that's not what I wanted to click on. It is working. Yay! All right. In that case, let's bring that up. Let's bring that up. Let's start doing some math. Uh-oh. Yeah, okay. We're good. Cool. All right, so sorry for the late start, but we're here now. So let's start doing some differential equation stuff, since that's what I had a request for. So differential equation just means an equation that is defined by derivatives. So for example, we can do y equals the derivative with respect to x of x squared. That is a differential equation. It's a very simple differential equation, and we can actually evaluate that one because we know how to evaluate derivatives. Y equals, and the derivative of x squared is 2 times x to the 1 equals 2x. So this is, in essence, what a differential equation is. It's just something that's defined by derivatives. It gets to be a little funnier if we were to say, for example, x equals d dx of x squared. Now that's a little bit more weird, but we can still solve this because this is just x equals 2x. And this actually doesn't ever work. Because then we have 0 equals 2, which is false, except for when x equals 0. So this equation is false everywhere except at x equals 0, and you end up with the delta function, which is a little strange, but we were able to solve it pretty quick. You just evaluated the side and you're good to go. When you start dealing with multiple variables, it gets to be kind of funny. We can still deal with it though. We have, for example, 3dy equals 2dx. That's a valid differential equation, and we can solve it. This one's probably easiest to do by separation of variables because it's already in that form. So we can integrate both sides. So we integrate, and I do it by notating this whole thing. So we'll do the integration of 3dy equals the integration of 2dx, which turns into 3y equal to, I'll do it so that you're more familiar with it, plus cy equals 2x plus cx. Now these constants, I wrote them separately because you're used to seeing them that way. However, it's just a constant, and there's nothing defining what that constant is going to be yet. So what we're going to do is I'm going to combine these into one constant instead of two, and I'm going to say this is just some arbitrary constant. So we'll turn from that into 3y equals 2x plus c. And then we can evaluate for just y. If I divide by 3, 1/3 of that whole thing is y equal to 2 over 3x plus, and I can write c divided by 3, but c is just a constant. You divide it by 3, it's still a constant. And so for the sake of writing it all out, we end up saying this. And this is valid because we don't care what c is. We just know that we have a constant out there. Don't let that part trip you up. If it really matters in your brain and you're having trouble understanding that for now, just do it all out. So if I was going to do it that way, I would have said 3y equals 2x plus cx minus cy. 3y equals, nope, I'll divide the whole thing by 3. Y equals 2x over 3 plus cx minus cy over 3. And that would have been my answer if I wasn't comfortable combining all of the c's. Those are all equivalent quantities in the green. So let's pick a slightly more complicated one. That one was, where did we start with? We started with this. So let's make it a little bit more interesting. We've got maybe 3y plus 2 dy equals 7x plus negative 4 dx. It's already in separable form because we have the x's on one side, the x's and dx's together on one side. So these are together. And the y's and dy's are together on one side. And since they're in that form, it's easy to just integrate the whole thing. So then we have the integral of 3y plus 2 dy equal to the integral of 7x minus 4 dx, which leaves us with 3y squared over 2 plus 2y plus a constant equals 7x squared over 2 minus 4x plus a constant. I'm going to combine my constants. And then we can try and solve for y. I'm going to multiply through by 2 because I don't like having these fractions in here. So I'll have 3y squared plus 4y equals 7x squared minus 8x plus c. I just let the c absorb the 2. And then I have 3y plus 4 times y equal to x times that one gets to be a little more fun. We use a quadratic formula here. 8 plus or minus the square root of 64 minus 4 times 7 times, let's see, it's negative b plus or minus the square root of b squared minus 4ac. I still have to write it all out. I don't just have it in muscle memory. Don't worry if you don't. It's fine. Over 14. And we probably don't need this. I'm just doing it because it may be useful. 4 times 7 times c, so that's what? 28 c over 14. Equals 8 plus or minus the square root 2 times the square root of 16 minus 7c. 14 plus 4 plus or minus 7. Yeah, now we'll leave it in this polynomial form because it takes longer to write the other. And for the purposes of your class, this is probably sufficient. And I don't remember really how to go any further than that. Or if it's even necessary. It's probably not necessary in most cases. We can do another one where we have 3x y minus 4 dy equals dx. I think I set that up right. So then we'll distribute in the dy, so we have 3xy dy. Nope, I did not. That's not what I wanted it to be. But now we have this extra x in with the y's, and we need it to not be. So we're going to divide by x. And we'll end up with 3y dy minus 4 over x equals 1 over x dx. I don't remember for sure that I can do what I thought I could do, so I'm gonna start this one over. So we'll do 3xy dy equals dx, and we'll run with this one. So we have 3xy dy, we'll divide by x again. We'll have 3y dy equals 1 over x dx. And now it's in separable form, so we'll integrate both sides. Integration of 3y dy equals the integration of 1 over x dx. So the left-hand side becomes 3y squared over 2 equals, and then this side becomes the natural log of the absolute value of x plus a constant as long as x is not equal to 0. Ow. And then we have y squared. We'll multiply the whole thing by 2/3 equals 2/3 natural log absolute value of x plus a constant. We just want y by itself. So what if x is 0? We need to know what that condition is. So we plug in 0 to this original equation. So 3 times 0 y dy equals dx. So this whole side goes to 0. So we don't know what's going on or where it is when x is 0, but we know that dy, no, not dy, dx is 0 when x is 0. So that's good information to have. If we rearrange and do 3 times 0, let's see, can we? I'm not sure if we can get any extra information out of that. And now that I'm thinking about it, I think it's fine because we have this limit helping to take care of things. So this is valid. And you can't take the natural log of 0 anyway, you'll get negative infinity, so yes, this is fine. Now, let's see. We could be given something in this form, dy dx equals 3x squared y minus 2xy. And this is still separable. How do we know this? It's because we can factor everything out. So we have dy dx is equal to y times 3x squared minus 2x. We can separate them. So you have dy 1 over y, so we've divided by y equals and dx, or multiplied by dx. So then we have 3x squared minus 2x dx. And then we do our integration again. So we have the natural log of y equals 3x squared becomes x cubed divided by 3, so our 3's will cancel, minus 2x squared over 2. And it looks like I planned that, and I totally didn't. Plus c, so then we have the natural log of y equal to x cubed minus x squared plus a constant, which is nice, but we're really more interested in what is y. So I'll write it again. We're really more interested in y by itself, so we'll raise this whole equation and put it on top of e. So we have e to the natural log of y equal to e to the x cubed minus x squared plus c. The e and the natural log cancel and leaves us with y equal to e to the x cubed minus x squared plus c. Yes. Which is kind of fun. For your sake, I will highlight the beginning and the end point. Okay. So that one's separable. What about one that's not separable? I'm going to put on my thinking cap here to try and figure it out. Let's see. If we have x, that's not the color I meant to have. 3x squared dy dx minus 4y equals 2y minus 3. Well, I know that this is not separable, but I have to show you that it is not. And the way I will do that is multiply by dx through the whole thing. So I'm going to do this in a different color. I think I'll do it in red so that you know it's not going to be correct. So I'm going to divide, I'm going to multiply by dx. So I've got 3x squared dy dx. I'm left with dy minus 4y dx equals 2y dx minus 3 dx. Well, now I've got a whole bunch of dx's and they're multiplied by y's. That, this right here, is how you know it's not separable. So the correct way to solve this one is to identify that it's linear. If you can get, if you can consolidate all of the y's to be by itself and have a dy dx, then you'll have 3x squared dy dx minus 4y, and I'm going to move this 2y to the other side. Now combine. And now is the crucial step. You've got to turn this section, highlighter, you've got to turn this coefficient into a 1 to make this work. So we're just going to take that and divide by it through the whole thing. So 1 divided by 3x squared leaves us with 1 times dy dx minus 6 divided by 3x squared times y equals negative 3 times 1 over 3x squared. That's a 2, that's a 1, that just becomes a negative 1, so we have dy dx minus 2 over x squared times y equals negative 1 over x squared. So now we have to find our integrating factor. Our integrating factor is right here. Integrating factor. By the way, this one is a linear equation. Linear ODE. So since this is our integrating factor, we're going to take that and we're going to put it on top of e to the integral of that integrating factor. So take this, put it there, and that gives us e to the negative 2 times integral of x to the negative 2 dx equals e to the negative 2 times x to the negative 1 over negative 2. And we will ignore the constant because here we get to just choose, so I'm going to pick 0. So for the sake of completion, plus 0. So this becomes e to the 1 over x. And that's going to be our integrating factor. So I'll correct this. That's not the integrating factor. This is the integrating factor. we just use this part right here to find our integrating factor. So our next step is going to be to take this integrating factor and multiply it through our whole equation. So we have this over here, and so we'll do e to the 1 over x times the rest of our equation, dy dx minus e to the 1 over x times 2 over x squared y black please is equal to, and again, e to the 1 over x times negative 1 over x squared. And this is where we start to be able to solve. Now, if you recall from Calculus 1, you have the derivative of u times v equals u v prime plus u prime v. That seems to be what we have here. We have u equal to negative 2 over x squared e to the 1 over x, and v equals y. So then you have du equals e to the 1 over x. Is that right? Nope, got it backwards. It's that. So u is e to the 1 over x, du is negative 2 over x squared, e to the negative 1 over x. And then that gives us dv equal to dy dx. So now what we can do is we can say, since this is the other form, we'll use that on this side. So we have the derivative with respect to x of e to the 1 over x times y equals that. Then when we integrate with respect to x, we end up with e to the 1 over x y. Yeah, let's write that correctly. Equals this integration. Which I don't care to do, but you could work it out. And if you worked out that integral, you would end up with the correct answer. The important part here is not what goes here. That's not as important as knowing to do the integrating factor. That's the key step with this one. Page. What else can we talk about? Maybe some linear algebra. Linear algebra is fun. Let's just talk about a problem that I've had doing robotic stuff. If I have a spot there and a spot here, I'm going to color code these, that way you know which one's which, because it does matter. We'll have a green spot, we'll have a blue spot. And then we will have another dot here that's going to represent a robot, or an observer. And this is going to be observing. Wow, I cannot. There we go. Let's redo this diagram. We have that line. This line. And for each one of these, we have some observation, azimuth, and elevation angles. Off of a true bearing. So we'll say that way means north, for example. And so off of that we have a theta 1, and over here we've got theta 2. Actually, I'll make that phi. Nah, now we'll leave it. And this is phi 1, and this is phi 2. This is towards P1 and P2. I want to know, where am I? And I have coordinates for this: x1, y1, z1. This is x2, y2, z2. And I want to know what is my x, y, and z. We could work that out with trig, but it gets to be kind of ugly, especially if you ever try and do it with more than 2 points. This is the power of linear algebra. So I'll work it out with 2 and show you how we can expand it to more than just 2. First thing I'm going to do is I'm going to write P1 in vector form, matrix vector form. X1, Y1, Z1, P2 equals X2, Y2, and Z2. And then our X bar is equal to X, Y, and Z. A little note about my notation. Notation convention. If I use a hat, for example, that's a unit vector. If I do not hat, like that, that's a vector of any length. If I do a bar, and I try and make it capital and bold, that's a matrix. And I try not to reuse letter names, but just for reference, that's how I tend to write things. So I want to know where I am in XYZ space. And I have the location of those two. And I have these angles. So I know that P1 is equal to X plus some length, we'll call it L1, times a pointing vector. What am I going to call that one? Call it V hat. Now V hat is related to, how did I write that? It's equal to the conversion of 1 theta 1 phi 1 in polar, and we need it in rectangular space. So how do you convert from polar to rectangular? I don't remember, but Google knows. Polar to rectangular. Nope. I want the yeah. We'll let this be positive y. It's a right-handed coordinate system. Yeah. So this will be, that'll be plus y. This will be plus x, and this will be plus z. So we'll say it is 1 in magnitude, so I can actually ignore that part, but it'll be 1 times that's not what I wanted. Coordinates. There we go. There we go. 1 times sine theta cosine phi, and then 1 times sine theta sine phi, and 1 times cosine theta 1. So that is our converted V. So this will be V1. So then we're going to have our equation in general, Pn, so this is 1, where n is 1, 2, 3, etc., equals x, x plus ln times vn hat. And that'll be the case for all of the n's. So n equal to 1, 2, 3, etc. Now we're interested in where x is. So what is x? Well, x is equal to Pn minus ln times Vn hat, right? For all n equal to 1, 2, 3. But we don't know what ln is. If we knew ln, we could find that because we're supposing that we know where pn's are. So we're supposing we know that, and we're measuring that. So we can, if we could calculate that one, we're good. Problem is, we can't calculate it with just one, but we can calculate it with 2 or more. How might we do that, you say? I'm glad you asked, because that's the fun part. That's where the linear algebra comes from. So what we're going to do is we're going to say oh, I have to think now. It is all of the x, or yeah, so we'll have multiple x approximations. So we have x we'll bear this general equation in mind, and we're going to use 1 and 2 for now. So x equals p1 minus L1 times v1 hat. X is also equal to p2 minus L2 times v2 hat. This should all feel fairly familiar to you because this is just like solving a regular linear equation, y equals mx plus b style. All I am doing is writing in some extra vector stuff, but that should be fine. So now what I'm going to do is, since they're equal, just like we would with y equals mx plus b, we're going to set these two equations equal. So we got p1 minus L1 times v1 hat equal to p2 minus L2 times v2 hat. But we're going to need L1 and L2. So let's try and solve for them. We get P1 minus P2 equals L1 V1 hat minus L2 V2 hat. Which makes you go, what do we do now? Well, since we're dealing with vectors and matrices and stuff, we have to remember that we can combine L1 and L2 into a matrix, a vector, if you will. So we've got P1 minus P2 equals L1 minus, L1 and L2, negative L2, times V1 L1 and L2 times V1 minus V2. So we'll call this L1, L2 equal to R, and that'll be a vector. So now we've got P1, P2 equals R times V. 1 minus V2. Which we can then rearrange a little bit. Now you'll have to put on your linear algebra thinking cap again. We're interested in R by itself, not this whole nonsense. So we're going to take this and quote-unquote divide by it. But in linear algebra, you don't have division, you have multiplication by the inverse. And you have to pay attention to which side it is. So we're going to say P1 minus P2 times the inverse of V1 hat minus V2 hat on the right. And we're going to use the pseudo-inverse because this is not going to be a square matrix. So this is going to, using the pseudo-inverse here, is going to give us the least squares solution, so the place of closest approach of all of these vectors. So what we'll end up with is, hopefully I can make this look decent. Stop that. So we'll have P1 minus P2 here. P2 minus P3 here. No. Ooh. How did I do this? I'm going to refer to some code that I wrote to test all of this on my off screen. Of course, I did not complete the code on this computer. It's fine. We have that, and then this is I'll have to review this so that I don't steer you wrong, but this part is correct. If you were to evaluate this, you would end up with a range for R. Once you have this list of ranges, which is what it'll end up being, is a vector of ranges, I just take the average when I do that. And then you can plug this R back in, because you know, again, X equals P N minus L N times V N hat. And so you'll pull Ln out of R and put it in here, and that will give you an approximation for your X, which is your coordinate location. And this executes really fast in code, and if I had planned ahead a little bit more and realized I was going to end up doing this, I would have code to demonstrate it. But as it is, I do not. It is on my other computer, and I didn't copy it over. So I don't have that. But it's been right about an hour, so to give my brain a break, and since I'm forgetting some stuff, I'm going to call it here. If you have any other questions, pop them in my Discord. Put it in the whiteboard channel, and I'll either get to it next time or try and answer you in the Discord. If you have any questions about this fun little robot thing, let me know, and we can try and do some more of this stuff. Maybe next time I'll have my code transferred over, and I can actually show it to you in operation, because it's pretty fun. It's really useful for doing indoor localization with robotics. I have yet to actually build a thing that uses it all and finds the tracks, because that's a little more entailed than I've done yet. But I'm hoping to have that put together eventually. So, unless I get any questions in the chat, it doesn't look like I'm going to. I'm going to call it here, and we'll see you next week.